Good morning, good afternoon, or good evening, whenever you're watching this video. Let us continue our discussions on electromagnetics. We'll discuss about capacitance, inductance, and energy stored in these devices. To start off our discussion, let us try to prove the capacitance in the parallel plate or two-wire line in that of a coaxial cable, and ultimately try to find the energy stored in these devices. The moment we mention capacitance, what comes to our mind is two parallel plates connected across the terminals of a voltage source. And you know that the moment the positive terminal is connected to one of the conductive plates, it accumulates positive charge, and the other plate accumulates negative charge. And the potential difference over here is going to be the difference between the potentials at the two terminals or at the two leads over here, and that is going to be given by the negative line integral from 2 to 1 of the electric field. So you know that from the positive to negative, some electric field is going to exist through the dielectric. And as per a definition, we know that the charge that gets accumulated here is going to be directly proportional to the voltage that gets applied, which later on we define as charge gets equal to a proportionality constant times voltage, and that proportionality constant is what we define as Q by V, or the capacitance. Now, to compute the value of capacitance, we have two methods in place. We can either go ahead and assume a value for the charge and then determine the voltage in terms of charge. We probably apply Gauss law here. Or you can go ahead and assume the voltage, determine charge in terms of voltage using the Laplacian equation. Let us choose method 1 for the time being, and we're going to assume a value for charge, and we will determine the value for voltage in terms of charge using Gauss law. And to accomplish this task, we first need to choose an appropriate coordinate system depending on the kind of device and its placement in three-dimensional space. And then we assume the charge plus or minus Q, compute electric field by using Coulomb's law and Gauss law, and then we find the potential, and then ultimately we go ahead as per definition and try to compute the value for capacitance. Let us go ahead and assume the parallel plate capacitance that we've been starting our discussion with. So let us go ahead and try to assume a coordinate system for the parallel plate. So, as in general, the easiest coordinate system in this case is going to be the XY plane. And let us assume that the plate is kept at a distance of d from each other. So, the x on the x-axis, you have the distance between the parallel plates, and you know that there is the electric field and all these things happening through. Since parallel plates have some charge, we can compute the charge density here, which we define as rho, to be given by charge by area. If we get a value for charge density, then the electric flux through a unit area, which we define as D, which again takes a value of epsilon E as per our earlier discussions, D over here is going to be negative rho in the AX direction. So if you just take a look that AX is upward because the unit vector going upward, but you see that the electric field is coming downwards, so it is in minus AX direction. You can intuitively understand that from the figure, and applying this expression that D is epsilon E, our electric field here is going to be given as rho by epsilon in the negative AX direction. So this changed the value of voltage here and there. This in turn can be rewritten in terms of charge if, since rho here is going to be charge by area. So our electric field may also be expressed as Q by epsilon A in the negative AX direction. Given electric field, our potential is going to be negative integral. Now let us assume that this plate is at 2 at the position 2, and this plate is at position 1. Now obviously this is going to be at 0 and D, because the distance between the plates is D. In negative integral from 2 to 1 E dl. Now since we are speaking about the rectangular coordinate system here, our dl, or the differential length, in this case is going to be dx in the ax direction. So we have the electric field here. We can go ahead and substitute that, and we have the dl from the rectangular coordinate system. So applying these two into our expression, we get that the potential is going to be negative integral from 0 to D, because the plates are kept at 0 and D, times negative Q by epsilon A in the AX direction, which is E as a whole, times dl. dl here is dx times ax from the rectangular coordinate system. Now ax times ax is going to be 1, because they are both the unit vectors, and there are two negatives, so our expression is going to look like 0 to D times Q by epsilon A times dx. Now a closer look over here shows that Q by epsilon A is a constant here, so our voltage can be put up as Q by epsilon A times integral of x. Integral of x is x, so x within the limits 0 to D. So that's going to give us that our potential V is Q by epsilon A times D. Definition for capacitance, C is going to be Q by V. So Q divided by V, we just proved it to be QD by epsilon A. So you can cancel out the Q, and the epsilon A is going to go back to the numerator, or your capacitance C is going to be epsilon A by D for a parallel plate. So onto this coaxial cable, let us go ahead and apply Gauss law. So the charge that we are going to speak of here, as per Gauss law, is going to be epsilon times the closed integral of E ds. So applying our cylindrical coordinate systems and applying integrations, you get that your charge here is going to be epsilon times ER, because it radiates outwards in the R axis, 2 pi R times the entire length that we have here. So total charge enclosed is going to be epsilon times ER 2 pi R L. And since you have your charge here, electric field is going to be charge divided by, or ER is going to be charge divided by epsilon 2 pi R L in the AR direction. So this is just a rearrangement of whatever we did. Now that we have our electric field, we can compute the potential as negative integral from 2 to 1 of E dl. Then again, in this case, in this specific case, we're going to integrate from B to A of E, which we know is Q divided by epsilon times 2 pi RL in the AR direction, times the differential length. Differential length in this case is going to be dr AR, because in the R direction for cylindrical coordinate system, we have already proved this. So what we have here is AR times AR is going to be equal to 1. Q by epsilon 2 pi L is kind of constant, because we just have a dr to integrate over here. So we get something like Q by epsilon 2 pi L integral d to a of dr by r. So if we go ahead and integrate this value and apply your limits and your taking your negative inwards, or it is going to be logarithm of a by b, and minus, you take it in, you get your potential q as q divided by 2 pi epsilon L natural logarithm of b by a. Now this is a very interesting relation here, and from potential you just go ahead and apply our definition for capacitance. You get that this guy to be q divided by 2 pi epsilon L times the natural logarithm of b by a. So this is going to be look like q and q goes out there, this goes on top over here. So 2 pi epsilon L divided by the natural logarithm of b by a is going to be the capacitance in a coaxial cable, which is an interesting relation. Now, having proved these two, let us go ahead and try to compute the energy stored in the electric field. So as per definition, we have this information that energy, which we represent by W, in the electric field is what we represent by WE, is going to be given by the integral of VI dt, where V and I are instantaneous values of voltage and current respectively. So in an electrostatic field, current is going to be the rate of change of charge as per our earlier discussions, or it is in general going to be Q by T, which we know. So the rate of change of energy can be defined as voltage times the rate of change of charge, or I can say that dWe is voltage times the rate of change of charge times dt. From this I can mathematically, I just took this dt up here and cancelled out the common terms, or in turn I'm going to have dWe equals V times dq. Now dq turns out to be C times dV, because q is equal to CV, where as per definition, if we go ahead and apply this expression in here, we are going to get that the rate of change of energy is V times dq is C dV. And if we just go ahead and integrate this expression here on both sides, integral dWe is going to be integral C times V dV, because C is going to be a constant. So we will have energy is equal to C times V times dV is going to be V squared by 2, or in turn, now our energy is going to be 1 by 2 CV squared, which is a very important relation, that the energy in a capacitor is half CV squared. As per definition, we right now found that the energy in the capacitor is half CV squared, and as per definition, capacitance is epsilon A by D. Using these two relations, let us try to compute what the energy is going to be. So I'm going to say that half, I'm going to substitute epsilon A by D here, V squared times V squared. And again, by definition, we know that electric field is V by D. Now, applying this expression in here, we can go ahead and state that V is E times D. So our energy within the electric field is going to be half epsilon A by D times E squared D squared. So 1D here and 1D here can cancel out. I can say that this is half times epsilon times E squared times A times D. Now A is area, D is distance. So area into distance is going to give me volume, or I can state that the energy per volume is going to be half epsilon E squared, or the energy per unit volume stored in electric field can be given by half epsilon E squared. Is a very, very important relation. About capacitances, let us take our discussion forward into inductances. Again, in two wires and in coaxial, and we will go ahead and try to prove the energy stored in magnetic field. So the moment we speak about inductance, let us go ahead and consider a long iron core over which a coil is helically wound, which we generally call a solenoid. Now, if a current I flows through the coil, closed flux lines are formed. We already know that. So the total flux linkage, which we are going to express using the Greek word lambda, is going to be n times the number of coils or number of turns times flux. So phi is the magnetic flux and n is the number of turns. So the total flux linkage is going to be the number of turns times the total flux, or self-inductance. We define something called self-inductance by the letter L as the total flux linked divided by current I, or this is in turn going to be N phi by I. You can go ahead and state that L is N times d phi by di, or you can state that L is a rate of change of total flux with rate of change of current, or inductance is defined as the rate of change of magnetic flux to the rate of change of current. Having defined inductance, let us try to find the inductance of a two-wire transmission line or two wires. So let us consider two wires in space. One wire carrying a current in the positive Z direction and the other in the negative Z direction, spaced at a distance of d apart, and each of the wire has a radius a. The flux linkage to each of these conductor, I'm going to call it lambda prime for the time being, is going to be the entire length times integral a to b of b dr. Now for two conductors, if we have two conductors here, for both conductors together, the total flux linkage is going to be twice the flux linkage for each of these wires, or this is going to be twice integral a to d L times b dr, where b is given by mu I by 2 pi r. So my total flux linkage here is going to be 2 times L times mu I by 2 pi integral a to distance d 1 by r dr, turns out to be mu L I by pi, because the 2 and 2 cancel out. 1 by r is log d by a, so natural log of d by a. or in turn my inductance L is flux linkage by current. So total flux divided by current is going to be mu L by pi natural log of D by A in a two-wire line. L is mu L by pi natural log of D by A. Moving forward, trying to find the inductance in a coaxial cable. We already know what a coaxial cable is, which has an inner radius of A, outer radius of B, and all those things. We can find the flux density at any radius r as B equal to mu I by 2 pi r. Now, if a length of L is considered, the total flux linkage lambda is going to be L times integral A to B, B times dr, or L times mu I by 2 pi integral A to B 1 by r dr, which again is going to be mu L I by 2 pi natural log of B by A, or the self-inductance as per our definition is going to be the total flux divided by current. So this was the total flux. So from the total flux from the right hand side, you take an I down, whatever you have is mu L by 2 pi natural log of B by A. So inductance of a two-wire line is going to be mu L by 2 pi natural log B by A. Having proven the inductance of coaxial line and of two-wire line, let us try to find the energy stored in magnetic field. So as per earlier definitions, we have that the work done by the magnetic field, work done is going to be V times I dt, where V and I are the instantaneous values of voltage and current. So from Faraday's law, we have that the voltage here is inductance times the rate of change of current L di by dt, which we know from earlier days, where L is the self-inductance. So taking this substitution in there, our energy is going to be integral L times di by dt, which is V, times I times dt. So dt and dt cancels out. What we have is L integral I di, or L times I squared by 2. That is what we have as the energy in an inductor, half Li squared. Another important relation, the energy in an inductor is half Li squared. Now trying to find the energy within the magnetic field, let us, from our definition, since we know that L is magnetic flux over current, and we know that the flux over current is B times A over I, where B is the flux density and A is area. Applying this relation into the energy equation, half Li squared is going to take us to half B times A by I times I squared. So if I cancel out an I and an I, what I'm going to get here is half B I A. Now we already know that B is mu times H, and we know that I is H times L. So if we apply both of these expressions into our energy equation, our energy in magnetic field is going to be half times mu times h times L times A. Now this is going to be half mu h squared A L. And as earlier, A is area, L is length. Multiplying them, you get volume, or WH by AL is going to be half mu h squared, or energy per unit volume stored in magnetic field is half mu h squared. Another important relation. So a quick recap of what we did. We proved what capacitance is. We proved what inductance is. We proved the values for capacitance and inductance for the two wires and for coaxial cables. And we also proved that the energy stored in electric field is half epsilon E squared, and the energy stored in magnetic field is half mu h squared. We will continue in the next session. Over and out.